Welcome to Essential Discrete Mathematics for Computer Science, Basic Proof Techniques, Chapter 2. We'll begin with constructive proofs. Before that, we should discuss what a proof is. In Chapter 1, we introduced the pigeonhole principle. It's a very intuitive concept. If there are more pigeons than pigeonholes and every pigeon goes into the same pigeonhole, then some pigeonhole must contain more than one pigeon. We gave the example, an anecdotal example, of 8 dinner guests and showed that at least 2 of them had to be born on the same day of the week. Now, anecdotal examples are not proofs. We need to have some healthy skepticism, and proofs are what help us convince ourselves and others that our claims are true. So a proof is an argument that starts with some premises and uses logical rules to establish a conclusion. When we make claims, we often use predicates. Predicates are templates for logical statements or propositions that take one or more arguments. Predicates themselves are not true or false, but predicates can be evaluated as true or false once we assign specific values for arguments. So back to the pigeonhole principle. If there are more pigeons than pigeonholes and every pigeon goes into a hole, then some pigeonhole must contain more than one pigeon. The predicate nested in this intuitive statement is we'll have the argument pigeon A and pigeon B, and we want to check the predicate are pigeon A and pigeon B in the same pigeonhole. More formally, we would take 2 distinct points in the set x, x1 and x2, and we'd want to check if under our function f of x1 equals f of x2. Pigeonhole principle proofs are examples of a non-constructive proof technique. A non-constructive proof is when a proof shows that a solution exists without giving that solution directly. So back to our dinner guest example, we have 9 guests at a dinner. At least 2 must be born on the same day of the week. In this proof, we let our set x be the dinner guests. We let our set y be the days of the weeks. Our function from x to y will map the dinner guests to the day of the week on which they were born. Since there are 9 dinner guests and only 7 days of the week, by the pigeonhole principle, at least 2 guests were born on the same day of the week. So in this example of a proof, we show that 2 guests must share a birthday, but we don't actually tell you how to find the 2 guests that share the same day of the week. That is what we mean by a non-constructive proof. We know that the solution exists, but we don't actually tell you how to find it. This is in contrast to a constructive proof. In a constructive proof, we provide the solution directly, or we show that a property exists by giving an instance of that property directly. Let's begin with a claim, a very intuitive claim. Every 8x8 checkerboard can be tiled by dominoes, which are 2 by 1 rectangular tiles. The tiles of the domino are the same size as each square of the checkerboard. We're going to give a constructive proof that uses an algorithm. An algorithm is a detailed, precise procedure that can be carried out mechanically. In fact, we could even code up such an algorithm. How could we do this? We can think of the checkerboard as a grid, and we can give coordinates to each square in the checkerboard. For example, the upper left corner of the checkerboard, we can give that the coordinates 0, 0. And the lower right, we can give the coordinate 7, 7. So going across the first row, we could have 0, 0, the first upper leftmost square, the one to the right of it is 0, 1, next to that 0, 2, and so forth. Once we think of this checkerboard as a grid, we can give an algorithm to tile the checkerboard, and we can even give pseudocode to code how we would actually apply this algorithm. So now we can think of the checkerboard as having coordinates I and j. For example, the leftmost upper square is 0, 0. Next to it is 0, 1. So now for I, starting out with 0, while I is less than 8, we'll increment I. Then inside that for loop, we'll set j equal to 0. While j is less than 8, we'll check if when we divide j by 2, so we take the modulo, we get a remainder of 0. This is just another way to say that j is even. If j is even, what we'll do is we'll place a domino horizontally starting at the square ij. So for example, for I equals 0 and j equals 0, we will place a domino starting at the square 0, 0, and it will overlap the square 0, 1. Once we do that, we can increment j by 2. So then on the next iteration of the while loop, we'll check j will be equal to 2, that's less than 8. When we check 2 mod 2, we know that that will be 0 because 2 is even, and then we'll place another domino starting at the square 0, 2 horizontally. And we'll continue this going across the entire first row. Once we have j equal to 6, we will place a domino, but then you'll notice that once we increment that j by 2, j will be equal to 8. We'll break out of that inner while loop, and now we'll increment I. When we increment I, we will have I equal to 1, that's less than 8, and we'll repeat this process of going through each row of the checkerboard and tiling it horizontally with dominoes. This is an example of a constructive proof because we actually demonstrate to you how we can actually tile this checkerboard with dominoes. We could do this many other ways, but when we give a constructive proof, you just have to give an algorithm that satisfies the predicate for the property that you're claiming. And in this specific example, our claim is that we can tile an 8 by 8 checkerboard with dominoes. There can be more than one solution, and you just need to give one in a constructive proof. Let's do another example of a constructive proof. We'll prove the following theorem. Every odd integer is equal to the difference between the square of two integers. Before we try to prove a claim, it's really important to make sure we understand it first. So let's see if we actually believe this. So we can take the odd integer 1, and we want to show that this is the difference between the square of two integers. Well, 1 is equal to 1 squared minus 0 squared. And now the next odd integer will be 3. And we can see that 3 is the difference between 2 squared and 1 squared. 5, well, that's the difference between 3 squared and 2 squared, 9 minus 4. And we could carry on in this way. But the important thing to notice is that this isn't a proof. This is how we build up our intuition for proofs. But doing this exercise helps us because we can start noticing some things. So one thing that we notice is that these odd integers aren't just the difference between the squares of two integers. They're actually the difference between consecutive squares of integers. So we could actually use that in our proof. And that's what we'll do. So this is good for building up intuition, but it's not a proof. But we do have one key observation. Our key observation, and this is stronger than what we're even claiming in this theorem, is that the odd integers are the difference between consecutive squares. This is stronger than what we're claiming in this theorem, but it actually helps us with the proofs. So let's see. First thing we have to observe is, what is an odd integer? For any odd integer, an odd integer, so we'll say it's n, equals 2k plus 1 for some integer k. And another way to see this is that when we take 2k plus 1 and divide it by 2, we'll have a remainder of 1. So 2k plus 1 modulo 2 would be 1. So that's an odd integer. And we want to show that 2k plus 1 equals the difference between the square of two integers. So why don't we use that? So we had before that it had to be consecutive integers. So we can try to square k and k plus 1 and take the difference. So we have k plus 1 squared, and we'll subtract off k squared. K and k plus 1 are consecutive integers, and we just observed that the odd integer would have to be the difference between the squares of consecutive integers. Okay, so let's actually square this. So we have k plus 1 times k plus 1. So we're going to get k squared plus 2k plus 1. In order to see what I had just done, let's just put this on the side. If we square k plus 1 times k plus 1, I just want to review this algebra. We take k and multiply it, so that's where we get the k squared. Then that's where I get the first k squared. Then I take the k and multiply it by 1. That's where I get the second k. Then I do this again for 1. I multiply the 1 by k, and I add it. I multiply this 1 by the last one. Then when I add this, I get the 2k in the middle. So that's where I get the k squared plus 2k plus 1. And then I subtract off the k squared. Well, when we do this, we can cross off the k squares, and we can see that it just equals 2k plus 1. In particular, what we've just shown is that if we have an odd integer, which is expressed as 2k plus 1, we can actually show that it is the difference of k plus 1 squared minus k squared. And so this was a constructive proof because we actually showed you how to find the two integers for which it is the difference between the square of the two integers.